Right. So I'd like first to thank Yidun for his kind invitation. It's great to finally come to this physics department at Fudan and meet my colleague here. This also gives me the opportunity to introduce myself. So as Yidun was saying, I mostly work on integrable systems and quantum groups. I did my PhD on random matrix model a while ago with Ivan Kostov, that is now at BIMSA, so maybe you met him. But I drifted a bit. And about 2 years ago, I started a kind of side project with Yutaka Matsuo at the University of Tokyo. That is a study of the non-Abelian quantum Hall effect. So that is what I will be talking about today. Right. So I also have to apologize to Yidun because that's more or less the same talk that what you've seen back in November. So that there haven't been much progress. We've been busy with other things, other projects. But there's been something new that is maybe a better understanding of what we need to do next. So this is what I will show in the discussion at the end. All right. So if students are interested, I will actually give a course on the quantum Hall effect next year in spring semester. So yes, you're welcome to join this. So, so this is based on this paper that has since been published in Physics Review B. And well, so I was told there might be non-experts in the audience. So I'd like to start from the very beginning. That is maybe 2 centuries ago now, the classical Hall effect that was discovered by Edwin Hall in 1879, which is simply the observation of a transverse voltage for a conductor in a magnetic field that is due to the Lorentz force that is acting on the electron. So there's an accumulation of charges on one side of the material, and as a result, this creates some electric field. So you're expecting to see resistivity like this. So in the direction of propagation of the current, it remains constant, but in the transverse direction, you get something proportional to the magnetic field. Now, the quantum Hall effect instead refers to the observation of plateau in the resistivity for low temperature and strong magnetic field. So the measure resistance at the plateau is given by this very simple formula, h over e squared mu, where h is just a Planck constant, e the charge of the electron, and mu is called the filling factor, and this is a number that labels the plateau. So you have 2 types of quantum Hall effect, the integer one that was observed first by Klaus von Kutzin in the MOSFET, so a type of transistor. That's the picture on the left here with mu equal 1, 2, 3, 4. And then it can also take a fractional value that was discovered shortly afterward by Zui and Schormer in gallium arsenic sample, called fractional quantum Hall effect. And this mu takes a specific set of values. So not every fraction is observed, but just several of them. So since then, both effects have also been observed in graphene, for instance. Now, the integer quantum Hall effect is well understood. It has a simple quantum mechanical explanation that is, in fact, due to the impurities of the material. So these impurities have 2 effects. So first, they lift the macroscopic degeneracy of the Landau levels. So for those who don't know, these Landau levels are just the energy levels of electrons in the magnetic field. So they have some kind of degeneracy that is of the order of the number of particles that is lifted by the impurity. But it has also a second effect that is to turn these extended states that carry the currents into localized states that do not carry current. So because of that, they do not contribute to the conductivity, and you observe plateaus of lengths proportional to the amount of impurities that are just here, while you basically fill up all these localized states that don't contribute to the conduction. So this is something very well understood. This has actually been used to measure this ratio h over e squared. That's called the von Klitzing constant in metrology, for instance. Now, on the other hand, the fractional quantum Hall effect is something much more mysterious. It has a different nature that involves the interactions between the electrons that we neglected in the previous model. And it's a sort of liquid state of electrons. So as I said, these Philip factors take a specific set of rational values. The first sort of explanation, a bit of a big word, was proposed by Löffling in 1983. And what he did is somehow to guess the expression of an effective wave functions that have the correct physical properties. So this only applied to this Philip factor, one of the K is K part. And that's the Löffling wave functions that he proposed. Something very simple. You just have a random determinant that over K and then Gaussian exponential. But what's interesting in these models is that you also see excitations that are called quasi-Halls that have this type of wave functions. And these quasi-Halls, they will carry a fraction of the charge of the electrons and also obeys a fractional statistic. So in other words, they are anyons. So in this case, Abelian anyons, which means that you will have a phase that when you exchange it, you can see the phase appearing from this. Now, the models of the fractional effect with more general filling factors involve the so-called non-Abelian anyons. So now the statistics of these anyons, the braiding, what happens when you exchange them, is given not only from a phase, but a non-trivial matrix transformation. And this is a very interesting property if you want to implement quantum computations. Even more so that these anyons are actually topologically protected states. So they would be very good candidates to realize fault-tolerant quantum processes, for instance. But so far, there have been no observation of this non-Abelian anyon in condensed matter systems. On the other hand, they've been recently realized a bit artificially on quantum processors by a team at Google. This is this paper in Nature of 2023. So very roughly speaking, I think there are like three main approaches to fractional quantum Hall effect. The first one would be to do a numerical calculation using somewhat realistic condensed matter models. No, I'm not a condensed matter physicist, so I know nothing about it. I have nothing interesting to say about this. The second thing to do is to somehow follow the Löffling approach and do some direct proposal of wave functions with good physical properties. And these are usually coming from conformal field theory correlators, like Versumino-Witten models with affine Kac-Moody symmetry. So in fact, Bloch and Wen argue in their paper that the Kniznik-Zamolodchikov equation that this object satisfy is responsible for all the good properties of the wave function. But since it seems still a bit artificial, so the argument is that you find a wave function that is in the same universality class than the physical one, whatever that means in practice. And the third approach is using field theory, using 3D Chern-Simons theory. So this is maybe a bit more satisfying from theory point of view, but you lose a bit sight of elementary degrees of freedom. If you look at the Abelian fractional quantum Hall effect, you will take a U1 gauge group with double K being related to the filling factors. And if it's non-Abelian, so you take a UP gauge group here, and the filling factor is related to the Chern-Simons logo by this expression. There's also, I should mention, some kind of a bulk boundary correspondence between two approaches, the boundary of the Chern-Simons theory gives you a CFT. So the question is, what's new with our approach? So in this paper, we introduced a new quantum models for the non-Abelian fractional quantum Hall effect that is obtained as a diagonalization of a matrix model proposed by Dorey, Tong and Turner in 2016. So that's a model that describes these vortices in 3D Chern-Simons theory that corresponds to electrons dressed by flux that will participate in the quantum Hall effect. So with this model, we recover some of the known wave functions obtained as CFT correlators. You can also show the emergence of this Kac-Moody symmetry in the large N limit. So it somehow relates these Chern-Simons and CFT approaches. But there's something more interesting, I think, is that the Hamiltonian of our quantum system is some kind of spin version of the well-known Calogero Hamiltonian. I will show expression later. Which is a well-known integrable system. And so at the time we wrote the paper, we expected this Hamiltonian to be also integrable. So there have been new results on this. I will keep the suspense and tell you this at the end. So is it integrable? Let's see. So this is interesting because we have a lot of algebraic techniques that have been developed to study integrable systems and do exact calculations. So this offers the perspective of doing exact calculation of quantities for the quantum model. So that's my introduction. Are there any questions so far? So here's the plan of the talk. I will start with the derivation of the models that use somehow standard matrix model techniques. So I will be maybe a bit brief here because maybe not everyone is familiar with this, and there's also nothing really new in this derivation. Then I'll present the model and discuss our results on the spectrum and the eigenfunctions. And finally, I will introduce a Fermionic formalism to solve some problem that we have over counting states, and also see the connection with Kac-Moody symmetry. Okay. So to understand a bit where the model is coming from, let's start maybe with a bit of history of this topic. So in 2001, Susskind proposed a description of this Abelian fractional quantum Hall effect using non-commutative U1 Chern-Simons theory at level K. Sorry. And shortly afterwards, Polychronakos introduced a UN matrix model as a regularization of Susskind's model to describe the microscopic dynamics of droplets of n electrons. By diagonalizing this matrix model, he found that the dynamics of the eigenvalues is governed by this Calogero Hamiltonian. And so basically what we did, roughly speaking, is to do the non-Abelian version of Polychronakos derivation. So in 2004, David Tong reinterpreted Polychronakos matrix model as a description of vortices in an Abelian commutative Chern-Simons theory. And following this interpretation with Patrick Dorey and Nick Turner, he introduced in 2016 an extension of Polychronakos matrix model with an additional UP symmetry to render the dynamics of vortices in the non-Abelian Chern-Simons theory in this case. So this is our starting point for work with Matsuo. So we diagonalize this matrix model and obtain the spin version of the Calogero Hamiltonian that involves order K symmetric representation of this UP symmetry. And this is somewhat a new model. So higher spin or higher rank Calogero Hamiltonian have been studied before, but higher order, I think, never. So that's something interesting. So let me give a bit of technical details on the derivation. So the matrix model of DTT describes the moduli space of vortices. So that's something that's represented by this quiver variety here on the right. Yeah, so we'll be brief. So you have just a gauge node, so you will gauge that. N is the number of electrons or number of vortices. Associated to this gauge node, you have this complex matrix Z. And then you have a UP frozen node that gives you, so it's like a flavor symmetry. And associated to this, you have this vector, n-dimensional vectors, you have here of them. So this is associated to the following matrix model that you see here. That depends on matter. So you have V, the magnetic field. You have here omega, the strength of confining potential. You see this potential here. And then K is the Chern-Simons law. The maybe new feature is that this model contains a non-dynamical gauge field alpha that enters here in this covariant derivative and also this term here. And this gauge field is here to impose the classical constraint that is written here. That is the Gauss law, or if you prefer the language of quiver variety, this is the moment map quiver. So, so in Dorey, Tong, Turner, they diagonalize the complex matrix and they find a different type of model that is, the Hamiltonian is somewhat simpler, but you lose again the degrees of, the elementary degrees of freedom. So the physical interpretation is easier if you follow Polychronakos' original approach, which is to decompose this complex matrix into the sum of two Hermitian matrices. So if you do this, the action takes this form here. Just replacing. This is the closed law constraint that I removed from the covariant derivative.
X1 X2 is real matrix.
Sorry?
X1 X2 or real matrix.
Yeah, Hermitian matrices, n times n. Yeah. So now we want to diagonalize this. So again, standard procedure. What we can do is explore the UN invariance of the model to diagonalize X1. And the eigenvalues of X1 will correspond to the position of the vortices of the electron. You also have this omega, this angular part of the matrix. You will end up having no dependence in omega in the physical wave function. So it will just drop. So the procedure is standard. So you cannot diagonalize X2 because they don't commute in general. So the diagonal part of X2 will correspond to the momentum conjugate to the X variable here, you can see. And the off-diagonal part will be responsible for the interaction. It is related to this phi here. The J part is associated to this vector field. So usual procedure, you compute the canonical momenta and you move from Lagrangian to Hamiltonian frame, and you get this expression. Yeah, so phi dagger in this expression will be the momentum conjugate. So far, everything is classical. So next you impose canonical quantization condition for xt, for phi dagger, omega phi. The only new thing is that you have a gauge constraint that you need to impose on physical states. And this you can rewrite it as these two constraints. So the first one just states that your physical wave function will not depend on the angular degree of freedom. And the second one is more interesting because you see that this JAA becomes a grading operator that counts the modes phi A. And so this tells you that this K here, this variable K, will be quantized because it's a mode unit. So this is how you get the quantization of the Chern-Simons level when you move to the quantum.
The conjugate momentum.
Oh, I had to take some linear combination of complex. Yes.
So it's the conjugate momentum of K.
No. JB, no, it's conjugate momentum of this omega. But you have to take maybe linear condition of omega and with the upper triangular with lower triangular, something like this. That's why.
Omega. I think so. Omega. So it has this AB indices.
Yeah, exactly.
So what? There is only one omega. Why there are two different?
Yeah, so linear combination, I think upper triangular and lower triangular. So this is a bit technical. I didn't want to write the formula. I can show it to you if you want to talk, but yeah, you have to do some silly manipulation like this. Yeah, I don't have on the top of my mind, but it's just a linear combination of maybe just omega and omega dagger or something like this.
So theory is some kind of curve.
Yep. Okay. Now, when we do matrix model, we always have van der Waals determinants that pop up here and there. There's no exception. When you diagonalize the X1 matrix, you have this. So as a result, your momentum should act on wave functions in the way conjugate with the van der Waals. So taking all this into account, we find the following Hamiltonian that acts on physical states. So you can remove the pi because pi on physical states they give you 0. And so this is the momentum. This is the Gaussian profiling potential, and then you have this interaction. So we will actually get rid of this van der Waals simply by conjugating the Hamiltonian. So you have to keep in mind that the wave function have some extra van der Waals in front of them that I will remove here. So let's try to discuss a bit this Hamiltonian. Is there any other question on the derivation? So let's see. So the model depends on the following parameters. So N is the number of vertices in Chern-Simons. It was the size of this Z matrices or X matrices, or the number of electrons, if you want, in the quantum Hall effect. P is the rank of the non-Abelian symmetry, UP. K is the level of Chern-Simon theory, so the two combine to give you the main factor. And then B is the magnetic field that is also encoded in the strength of the magnetic. It's also encoding the strength of the confining potential, because you see that it is, yes, I forgot to mention that. We have this factor omega over the square here that we will also drop from the model. Now B, you see, encode the strength of this confining potential. No more omega. So the model describes n particles of color XA that carries a representation of the UP symmetry. So the spin structure is introduced using this bosonic oscillator that obeys canonical conjugation, canonical commutation relations. So they have this UP index from 1 to P and the AB index from 1 to N. So here at each level k, the particle will carry a state that is built from k oscillators. So there will be k spin indices I1, 2, ik here. So this is the constraint that we had from the Gauss law, the GAA on physical state equals k. State. So this tells you that each state should carry k oscillator. So this is the higher order symmetric representation of PP. So symmetric because these phi dagger they commute, so you can exchange them. Yeah, I should mention that physically this spin may not be a physical spin. This can encode a band structure or presence of higher Landau level or other kind of physical properties. So it's more like an effective spin. So here's the Hamiltonian of the model after cleaning things up a bit. So you recognize kinetic term, a quadratic confining potential, and then this interaction term, or 1 over x squared, that is typical of Calogero models. And this JAB, it's easy to check that they satisfy the GLN relation, computation relation. Here. This model also has a global UP invariance that is generated by this K here. So here you're summing of the particle index, spin index 3. And for the same reason, they obey the GLP commutation relation. So this product can be used to decompose the Fock space into symmetry sectors according to a UP invariance. But we will not do this. It turns out not to be so useful for this model. We kind of forget about it. We tried, but it didn't work so. Okay, so to get a sense of the model, let's examine some specific values of P and K. So first for P equal 1, so this is the polychronacos model, and we recover the Calogero-Hamiltonian that describes the Abelian model. So the kinetic interaction term is just constant K plus 1 here. That is a very well-known integrable system. Now, when K equal 1, the particles carry only the fundamental representation. You have only one oscillator here. And the interaction term simplifies. You can rewrite it using permutation of spin. And you end up with the spin Calogero model that is also maybe less well-known integrable system, but certainly integrable. In addition, it has a quantum group symmetry, a Youngian symmetry at planet N. Yeah, so that's a very remarkable property. So this can be used to write down the eigenstate in terms of representation of the Youngian. Oh yeah, I should mention also the trivial case. So when K equals 0, particle has no spin degree of freedom, the interaction term vanishes, and you just have n decoupled harmonic oscillator. You just have a Slater determinant for the wave function. So before I start talking about the spectrum, I need to make some technical remark that will simplify a bit our life. So first, I want to conjugate with this Gaussian factor here. So instead of having the quadratic potential, now you have a linear derivative term, also a constant, that's not too important. So all my wave functions, they will have a common Gaussian factor that I will again omit. I will not write it down here. And then I will also rescale the coordinate and the energy in such a way that I can set P equal 1 in the model. So there's no more parameters now. So now let's diagonalize the model. So again, a few technical remarks. So first, I'm going to use polynomial representation for the spin states. So I don't know, this is usually classic, but I don't know if you see this. So instead of using this question operator acting on the vacuum, I will use represent this as the monomial in the y variable. So the y carry the same indices of spin and particle index as the phi diagram. And in this representation, the phi, the conjugate, is just the formal derivative. So by doing this, I can express my wave functions as polynomials in x and y. And the fact that every state carry k oscillator means that this will be homogeneous of degree k in y for each of the particle A. So now we're working with polynomials. That's much easier. Next, I want to introduce something called wedge states that are just n times n determinant as follows. So on the yes, I don't know which one is which. So the excitation here will depend on the spin index and the polar index. This column index corresponds to a variation of excitation. And the row index is the particle index, the particle 1, 2, and you can rewrite this determinant in terms of the wedge product. It's convenient notation. So this just denotes the columns. So you forget about the particle index, and you just have the index for the excitation. So here we have N1 and 1 for control, IN the other one. And so this will be labeled by n tuple of integers. We put the same trick as blue block. Instead of carrying all the time index I and n, we group them together in a single number, where so from this number you can take the Euclidean division, and the quotient will correspond to the power of x, and the remainder to the spin here, so between 1. That's again a convenient trick to not to have to carry in every time, but just a single number. So of course the determinant will vanish if two columns are the same. So if two R numbers are the same, and we can also order them in this way to not to overcount them R1 and R2. No. So we only choose the number such that it doesn't vanish. So we always take R to be different. So this is all good for k equal 1. But for k greater than 1, we need to do a little more. We need to take product of these wedge states. So a product of k states. For some reason, I reintroduced the one here. So now you will have k tuples of p integers. K tuples of n integers, not p. Yeah, n integers. There's a typo here. So you have an extra index alpha, a Chern-Simons index from 1 to k. So of course you don't want to overcount states. So you will assume that if you reorder R alpha, you don't get a new element. So you quotient by the permutation group. So there's a natural grading on this that is just the homogeneity in the x variable that you can define. So this just counts the NA for every particle and for each of these factors. Now, there is a big problem here is that these wave functions for k greater than 1, they are not linearly independent. There are known relations between determinants, like the Prucker relation for k equal 2, and that is determinant probability. So we have a problem of overcounting states here. So I will come back to this in the last section. This is why we need to introduce this Fermion language. So here's the main result of this paper. So we prove that the Hamiltonian has a triangular action on this function, this product of wedge states, where we have coefficients that we can determine. So this can be immediately inverted to give you the eigenfunction. Here, where B is just determined directly.
Triangular action is decomposable.
It means it is yeah. So this is just a triangular matrix. For lower frequency.
So basically, it's decomposable.
Yeah. So the thing is that this gives you directly the energy spectrum because there are the values on the diagonal, and this corresponds to this gradient. This you see they are organized on gradient. The proof was a bit painful, I should say. It's about expanding these determinants by rows and columns and resumming things. It's a bit technical. There's actually a better way of seeing this. I should also mention that by some naive power counting argument, we expect that in the larger limit, so in macroscopic limit, this wedge state psi will become the true eigenstates of the models. So before talking about wave function, I would like to make a short and cute remark that was actually talked to me by Yihao Zhou, that is now at SIMIS as well. He worked on this and wrote something quite interesting. I will comment on their paper at the end. So they did this after our work.
To refer to FL2Z or
No, Lie algebra SL2, everything is over the complex. SL2C, it doesn't really matter. You will see. But next slide. Other one after. Yeah. So let me see. So let's recall the expression. So the original Hamiltonian here with the term H. This was the gradient operator, and this is just the conjugate by the Gaussian, and this is the same, but you have no quadratic term and the linear term. So this is what I mean by SL2 triplet. You have three operators that satisfy this SL2 and the algebra relation. It doesn't really matter if you C or R on the level of the algebra. So if you define the operators as follows, so take E to be this quadratic term, F to be the Hamiltonian without the quadratic term, and H to be the gradient operator, then you can show that they satisfy this algebraic relation. So the first and the third one are very easy. The second one a bit more difficult. So if I reformulate my Hamiltonian in this language, we started with something that is F plus E. You conjugate by E, and you get something that is F plus H.
Remember, you set E to be 1. At some point.
E to be 1?
You set B to be equal to 1.
Ah, yeah, I put it back here. Yeah, so you could take B to be 1 here by rescaling it. Yes. But I wanted to have B. Why did I want to have B? Sure, I must have had a reason why I wanted to have B here. Yes, but you can put it to 1, I mean, the same argument. Yes, so right. So this is quite interesting for the spectrum here, because you can rewrite the Hamiltonian as a conjugation of H by F. And these wedge states, they are eigenstate of H. And so the eigenfunction of this Hamiltonian is just the action of the exponential of F over this psi here. But F is an impotent operator, which is SLT. So if you expand this, you will have only finitely many terms. So this means that you can obtain the true wave function by starting with the simply the wave state and applying F just a number, which is indeed. So this is also explaining why you get this triangular structure. I think that's quite cute, but it's just personal. No, unfortunately, no. I don't know how much more time I have.
We started, but we have 20 minutes.
20 minutes. I'll do my best. We'll see. Yeah, I might go more quickly on the fermionic part. So we have more results. So from this, we also, since it's triangular, get the ground state expression. So when k equal 1, the ground state is unique, is p divides n, and is given by this. So you fill up all the spin, and then you start increasing the powers of x until you reach say m minus 1. So n is p times m. So when k is greater than 1, you just take product of this. So you also have a singlet ground states. So that's an example for k equal 1, just a determinant. Now, what happens when p does not divide n, then the ground state becomes degenerate. So the same trick, you start filling up all the possible spin and x power. And then at the end, you have to choose the spin for an extra q particle, where q is the remainder by Euclidean division. So this is I1 to IQ, and this is where the degeneracy comes from. We can compute easily the ground state energy in this case. And when k greater than 1, you have even more degeneracy, but you have the nice property that the total energy is just k times the energy in each of that elements. So this all agree with DTT result. Another important result that should probably make Bloch and Wen happy is that we managed to show that these ground state wave functions, they obey this KZ equation that is written here, Knisling and Novikov. So this is a strong indication that you have Kac-Moody symmetry. So this was shown in Dorey, Tong, Turner with different methods, only when P divides N. So we generalize their result here. Try not to rush through it, but then we also have a general statistics. You can see that when two coordinates coincide, because you have spin variables, your determinant will not vanish. They will only vanish when you have p plus 1 particles that approach each other. So you have some kind of generalized exclusion principle for this.
But this is just like Abelian and
No, because these are vortices. I don't have the hole yet, but it looks a bit, yeah, so they are. So the thing is this, in this non-Abelian model, yeah, so vortices are anions here in this model. Yes. So they have some, and we can in this way also propose some wave function for quasi-hole. They would have this factor that is characteristic of the quasi-hole wave functions. So you can recover many known wave functions in this way. So for instance, the Moore-Reed wave functions, that is known to be a affine, corresponds to so now we have two remaining questions at this stage. The first one is how do we get rid of the extra states that come from this Pucker-like relation between the turbulence? And then can we observe the emergence of this Kac-Moody symmetry at that? And for this question, we use the free Fermion formalism and something that is connected to lower rank duality. So this is the last part. So that part is a bit more technical. I'll try to give you maybe mostly the main ideas. So first we'll do this at finite n. So we need to use non-relativistic fermions here.
Basically, your number of flavors.
No, P is the number of flavors. No. N is the number of vortices of electrons. Yeah. So you want to send n to infinity at the end to get something like that. So these fermions, they carry three types of indices. They have a spin label from 1 to p, Chern-Simons level label from 1 to k, and a mode number that is positive because it's non-relativistic. They obey standard commutation, anti-commutation relation. And you can build the Fock space as usual. So you take a vacuum and relate it by psi, and you build a state with psi bar. And you have several gradients, but we want to use the one that is indexed by the Chern-Simons, and that counts the mode psi bar I alpha n for each arm. The idea is that we have the same number of particles in each Chern-Simons sector. So we will have the n1 for k here. So that's the Fock space decomposition. We also have usual states, dual states that are annihilated by psi bar. Now on this Fock space, you can define the action of a lot of symmetry algebra. So this will be a positive part of loop algebra. So mathematicians would call this GIK times polynomial. So we have generators that are indexed by n with n positive only. So for instance, here you have UK plus. You can realize this action by taking this kind of convolution with the mode index, and then summing of a spin index, you get something that depends on Chern-Simons label, and then satisfy some UK commutation relation, but we don't. You have the same for if you know the trace of the Chern-Simons. If you don't trace, you have P times K, and you want the trace of the everything. And it's not hard to show that now we have, so this has been studied in the context of global rank duality and been shown by people that we have the decomposition of UPK to SUP, SUK, and U1, where SUK are defined as usual by right? If they have, you do this because UP and UK are the same U1 factor. This is all nice, but what does this have to do with our problem? So the thing is that these wedge states that can be realized as projection of the states in the Fermionic Fock space. So this state here, where the projector is constructed like this. So it's just constructed in such a way that we produce the determinant. And you can easily show that this projector has an SUK plus invariance here. And this is by portioning over this invariance that we can remove these states that we had. So to show how this works, let me give you the example of k equal 2 and recover this Pucker relation. So k equal 2, you have for SU2 plus 3 generators, L12, L21, and the diagonal part 1, 1 minus 2, 2. Fermionic state has this form, so you have the creation operator for k equal 1 and then k equal 2. So the first one is about n1 and n, and the other one n1 and n, and spin index I and j. So we can compute using the previous formula the action of L21 on these states, and we obtain this. So L21 remove a creation operator with k equal 1 and add one with k equal 2. And when you project this, what you find is exactly this triple relation. So this is how these relations come out from the SUK symmetry. Note that if you start with L12, you can find the same relation. And here, this will just produce a trivial identity. So you don't really have anything more than precursor relation for k equal 2. So this solves our problem. Now, 10 minutes. Yes. Now we can also use this to show the emergence of Kac-Moody symmetry in large N. So in large N, these fermions, they will become relativistic fermions. So it's the same story, but you now have modes that are half integer, so also negative mode. And now the vacuum is annihilated by positive modes and creation operator of -1. I'll be a bit brief on this, maybe, because I want to spend some time on the discussion. So you have the same type of generators, but now they are proper Kac-Moody algebra. So you pk at level 1, you had p at level k, you have k at level p, and so on. And you have this decomposition of common embedding. So again, studied in the context of level rank duality. And you can decompose the Fock space in this way. So first you have to decompose the U1 charge. And then you have for each fixed U1 charge the sum of the partitions that label both SUP and SUK symmetry. So again, the same kind of trick, maybe I'll skip this, but you have to reorder things a little bit, but you can show that you can take the larger limit of these wedge states. And yes, and then define a projector in such a way that, so this is the example of the little state. In such a way that this infinite wedge product of the projection of some state in the Fock space. So then the invariance by SUK plus is expected to be replaced by the Kac-Moody algebra. And yeah, so this means that if you quotient by SUK, it means that linearly independent eigenfunctions are spanned by SUP plus U1, and you recover here your Kac-Moody symmetry SUP at lower k. So you recover this in the spectrum. Okay, and you can actually show that this satisfies some. Yeah. So yes. So let me maybe summarize what we did. So starting from this matrix model by Dorey, Tong, Turner, we derived a Hamiltonian that described the dynamics of vortices in 3D UP Chern-Simons theory at level k. We introduced a class of wave functions as determinant involving both coordinate and spin dependence that are called wedge states. And we managed to show that the action of the Hamiltonian on the wedge state is triangular. So we deduced the energy spectrum and the ground state wave functions. We proved that the ground state wave function obeyed the physics Zamoračikov equation. And then we introduced this fermionic construction for wedge state at finite n to explain the overcounting of states by the presence of this loop algebra symmetry SUK hat plus. And then we discuss the large limit of the fermionic description and observe the emergence of this FUK Kac-Moody symmetry. Now, until well, recently, not so much anymore, the main question was the integrability of the model. But new results have been obtained by Sen Hu, Yihao Zhu, and Li and Ye, using a geometric construction of the Hilbert space and the action of what they call deformed double current algebra. So first, they proved the integrability of our model and also the Youngian invariant. But there is a twist because the Youngian must be conjugated by this F operator that you saw before. So this is why it was not obvious to us. Also because usually integrability is shown using Dunkel operators for Calogero model. And in this particular case, it doesn't work. So you don't have Dunkel operators, but you still have integrability and Youngian invariant. Then they managed to prove the emergence of Kac-Moody symmetry using the Youngian generators as n goes to infinity. They also studied the Calogero-Moser, so the trigonometric version of the model here with a spectrum of Hamiltonian. So they obtained the spectrum. They saw this scale-form setting pattern that come from the Youngian symmetry, for instance. And many more results. So it's a very nice paper. So what should we do next? Right? So the main difficulty maybe is that so far this model is restricted to the description of the first Landau level. And if we want to have all these nice topologically protected states, we want to include this quasi-hole, and we need to go to higher Landau level. And this is a difficult problem. In the Abelian case, for instance, this has been studied by Capelli and others extensively. So they have this Chern-Simons-Maxwell matrix model in this case that is somewhat represented here. So the thing is that so the extension to the non-Abelian case is rather trivial. You just have to add more vector fields here. Problem. The problem is that this quadratic term here makes the diagonalization very difficult. So they try to do different things, but it's not fully satisfying. So instead, since we are only interested in the first two Landau level, so we might have some simplification, some simpler model. And the most physically relevant part of this is actually the Gauss law that is imposed by this model that takes this form here. So the question is, maybe there's a simpler model with similar physical properties with the same Gauss law. And we might have for this some inspiration from gauge theory and the study of vortex moduli spaces that they did in this context. Now, from the CFT, from the Löffling wave functions point of view, Hamiltonian for including both vertices and quasi-hole for the Abelian model has been proposed. So this is for the Löffling wave function that I've shown at the very beginning. So you have this simple Hamiltonian that is just the sum of the Calogero model for the vertices and for the quasi-hole with different coupling. So the question is, could we derive this by from a matrix model? Could we, and then could we try to make it non-Abelian in some way? So for this problem, we seem to have all the different pieces of the puzzle, and we just have to put everything back together to get the picture. Now, the second question that's maybe more related to what Yidun is doing. So in this model, as you don't actually observe, these vertices have non-trivial statistics. They behave as anion. Now, the braiding of non-Abelian anion is usually implemented using modular tensor categories. And it's found that representations of quantum groups form this tensor category. So it's natural to expect that this Youngian invariance of the model that has been shown it has something to do with the braiding of this model. That's something we would like to understand. Now, this is great. We have integrability, but how do we exploit this to do something physical? Like maybe compound compare with experiment. So can we use this to compute correlation functions, to compute entanglement entropy, for instance? I know that in Forrester's paper there is some interesting computation, some correlators, I think. So maybe if we can generalize this to non-Abelian case, we can also get something out of this. There's a lot of a lot of deformation. So I mentioned the Calogero-Moser. There's a trigonometric elliptic deformation, a lot of deformation in the model. And also this kind of freezing limit of the Halden-Shastry kind of version. Construction of wave functions of Googloff that maybe can be also introduced for Sutherland. And then this connection with supersymmetry gauge theory and AGT correspondence. This was explored by this paper of Etienne Pasquis and Takira Serban that might also give some insight in our model, in particular on the role of this Youngian and toroidal quantum. So to conclude, so we expect that looking at this non-Abelian quantum Hall effect from the point of view of integrable model will offer new insights on the braiding of anions, and we're working toward this goal.
Thanks, Professor Bourgine, for the report. Ask any questions along the way. I hope general question.
Yeah.
Does this number have any relevance to QCD or some fields?
I'm no expert on this. So I'm a bunch of applications. You see, is a bit far-fetched.
Some complex model strings.
Yeah, but it's relatively simple integrable system, so you find it. So Calogero models, typically you will encounter them in common matter. Or in matrix models, because they're on their mark. They are connection with symmetric functions in mathematics. In string theory, it must appear somewhere. Which text explicitly, yeah, I'm pretty sure. Maybe something is really there. Yeah. You have this evaluation representation. Basically, no, you do. You have evaluation representation. So you have a spectral parameter. So in a sense, it's not finite dimensional because you have a power. No, but in practice, in physics, the parameter you cannot really introduce. So so it's just the usual. So evaluation representation are the usual algebra representation, so finite dimensional, where you multiply by some power of parameter. So it's we could see this physically as some finite dimensional plus a parameter. Yeah, I know in physics we don't have usually infinite dimensional representation. But this is actually related to the fact that we have a continuous coordinate in this model.
Yeah, I'm actually quite confused about the statement. What's this new insight in on radium annual?
Well,
I didn't really quite get it.
that's the presence of this symmetry algebra that we didn't know at finite limit, right? It's the Youngian symmetry that flow. So with this, we can build higher complex quantities, maybe do some kind of generalized Gibson model if we want, diagonalization. This, yeah, so this is just the beginning of the model, but I think that's the thing. And this should be somehow related to the Brownian. So this R matrix of this Youngian should have something to do with the Brownian relation of bubbles. So that's the
Think about all the young equations don't have this spectral plan.
Yeah, you use finite quantum group in this context. Yeah. But usually you're looking at some kind of simpler model. You don't have continuous coordinates. So here this Youngian appears by combining two things. Typically, I mean, here we don't have Dunkle operators, but so it combines the SLP algebra with the Dunkle operators that is related to the continuous coordinates. So it's some kind of momentum that would diagonalize this Poisson bracket if you in the classical model. So yeah, so this is the feature because you have to combine SLP to
You get lost.
Sorry. It's
If no more questions, I'd like to thank Professor Bourgine again. Yeah, this is what typically happens.
Yeah.
Given technical seminar. Everywhere.
Yeah, so I tried to make the first half non-technical, and then you have to present your results.
But this is his. Is this yours?
Yeah.
Yeah.